Newton's law of gravitation. Thanks for watching this video and don't forget to like, subscribe to the channel and activate the notifications. It is very important to the continuity of this channel. This video will introduce you to one of the fundamental laws of physics, Newton's law of gravitation. The law of gravitation makes it possible to calculate the orbits of the planets around the Sun and predicts the motion of comets, satellites, and entire galaxies, and the major tidal constituent is the Moon's gravitational pull on the Earth. Newton's law of gravitation was published in 1687. We have seen that Newton's second law implies that whenever a particle moves with acceleration, a net force must be acting on it. Similarly, a planet that orbits around the Sun also experiences acceleration, and thus a force is acting on it. Newton was certainly not the first person to realize that an apple falls to the ground when dropped from a tree, or that a planet turns around the Sun. However, he did recognize that the force that pulls the apple to the ground is the same as the force that holds a planet in its orbit around the Sun. Newton published the law of gravitation in 1687. It may be stated as follows. Every particle of matter in the universe attracts every other particle with a force that is directly proportional to the product of the masses of the particles and inversely proportional to the square of the distance between them. Translate this into an equation. We have the following equation. From Newton's third law, we know that the force exerted by m sub a on m sub b is equal in magnitude but opposite in direction to the force exerted by m sub b on m sub a, forming an action-reaction pair. R is the distance between their centers of mass. G is a constant called Newton's constant of universal gravitation. It has the following value. Calculate the gravitational force of attraction between the Sun and the Earth. To calculate the force between the Sun and the Earth, we apply Newton's universal law. We take the values and substitute them in Newton's law of universal gravitation. To use Newton's law of gravitation, the distance must be in meters and the mass in kilograms. We substitute known values of g and the masses into the universal gravitation equation, and solving for F, we get this value. Calculate the gravitational force of attraction between the Earth and an apple having a mass of 150 grams. We substitute known values of Newton's constant of universal gravitation and the masses into the universal gravitation equation. Solving for F, we get 1.47 newtons. If we calculate the weight of this apple applying mass times gravity acceleration, we get the same value because the weight is the force of gravity. Gravitational field strength. We can use the fact above to determine the gravitational field strength for a point or spherical mass. Let us assume that the Earth is a uniform sphere of mass m. The gravitational force from Earth on a particle of mass m located outside Earth, a distance r from Earth's center, is given by Newton's law of gravitation. However, this gravitational force is the weight of this particle. We equate the weight of the particle on Earth to the gravitational force acting on the particle to get the gravitational field strength G. we see that the field strength is actually equal to the acceleration of gravity. We can express the magnitude of the field strength in either newtons per kilogram or meter per second squared. However, if we are dealing explicitly with field strengths, then we tend to use the unit newtons per kilogram. The mass and radius of the Moon are given as follows. What is the gravitational field strength on the surface of the Moon? Use the equation for G to determine the gravitational field strength of the Moon. The gravitational field strength of the Moon is 1.7 newtons per kilogram. The gravitational field strength of the Earth is 9.8 newtons per kilogram. This means an object with a mass of 1 kilogram would be attracted towards the center of the Earth by a force of 9.8 newtons. The gravitational field strength of the Moon is 1.7 newton per kilogram. This means an object with a mass of 1 kilogram would be attracted towards the center of the Moon by a force of 1.7 newton. We feel forces like these as weights. My mass is 80 kilograms, and if we multiply by gravitational field strength 9.8 newtons per kilograms, my weight is 784 newtons. Now, if I go to the Moon, my mass will be the same, 80 kilograms. We multiply that by the Moon's gravitational field strength, which is 1.7 newton per kilogram. That means my weight on the Moon is 136 newton. So I have different weights on the Earth and on the Moon. That's why astronauts can jump high on the Moon's surface. They are lighter up there. The Earth has radius 6,400 kilometers. The gravitational field strength on the Earth's surface is 9.8 newtons per kilogram. Use this information to determine the mass of the Earth and its mean density. Substitute the quantities given into the equation to find the mass of the Earth. Use the equation density equals mass divided by the volume to determine the density of the Earth. The Earth is a spherical mass. Its volume can be calculated using the volume of a sphere. The mean density of the Earth is 5,500 kilograms per meter cubed.